Gaussian processes are the gold standard for uncertainty quantification in machine learning. They give you calibrated confidence intervals, principled regularization, and mathematically sound predictions. But there's a brutal catch. Exact GP inference scales cubically with your dataset size. That O(n)(3) complexity from inverting the kernel matrix means GPs effectively choke on anything beyond a few thousand points. You've probably heard of sparse GPs, which introduce a smaller set of inducing points to approximate the full covariance. That helps, but it still leaves you wrestling with O(n)(m)(2) scaling. And when you try to stack these into deep architectures or push them to high-dimensional feature spaces, the computational overhead becomes a hard ceiling. What if you could keep the mathematical rigor of GPs, but make the inference complexity depend logarithmically on the number of inducing points? That's exactly what SIKA-GP achieves. Let's break down how SIKA-GP, which stands for Sparse Inducing Kernel Approximation GP, actually pulls this off. The key insight is that you don't need to learn arbitrary inducing locations. Instead, you fix a structured dyadic grid of inducing points and exploit the mathematical properties of the Laplace kernel. Why the Laplace kernel? Because it's Markovian. That Markov property means the covariance function has a specific recursive structure that allows you to decompose it into a set of compactly supported, closed-form basis functions. Here's where it gets interesting. When you fix those inducing points on a dyadic grid, the GP prior can be exactly reparameterized as a finite-width Bayesian neural network. But this isn't just any BNN. The activation functions are explicitly structured basis functions that are non-zero only over local intervals. For any given input, you're not computing thousands of kernel evaluations. You're only activating a tiny subset of these basis functions. Specifically, at each dyadic level, only one basis function per feature dimension lights up. If you have L dyadic levels, you're only ever dealing with L plus 2 active units per dimension. That's the core efficiency gain. The full inducing set might have M points, but your effective computation scales as O log M. Now, how do you make this actually fast on modern hardware? Evaluating those basis functions naively would still be slow. SIKA-GP introduces something called Tensorized Sparse Indexing. Because the basis functions are tied to a fixed dyadic grid, you can compute exactly which basis functions are active for any input using simple arithmetic. You take your input tensor, multiply it element-wise by powers of 2 corresponding to each dyadic level, take the ceiling, and add a precomputed offset. That gives you a compact index tensor. You then use that index to slice directly into the weight matrix, pulling out only the random weights associated with the active bases. This entire pipeline is fully parallelizable and maps beautifully to GPU tensor cores. Instead of sampling a massive weight vector of size d times m, you're only sampling and multiplying a lightweight vector of size d times l plus 2. The variational inference stays exactly the same. You're just optimizing a much smaller, structured variational distribution over those active weights, maximizing the standard ELBO with flip-out reparameterization to keep gradient variance low. And because this BNN representation is so clean, SIKA-GP plugs directly into modern Bayesian deep learning architectures. You can stack these sparse GP layers to build deep Gaussian processes, or sandwich a SIKA-GP layer on top of a raised net, or a transformer to get deep kernel learning with uncertainty. The paper benchmarks this across regression, vision, and language tasks. On UCI regression datasets, stacking 2 SIKA-GP layers cuts training time by up to 7 times compared to dense DGPs, with 0 loss in RMSE or negative log predictive density. On image classification with CIFAR10 and CIFAR100, DKL SIKA matches or beats SVDKL and DAK baselines in accuracy and calibration error, while training 2 to 3 times faster. Even on transformer-based intent classification with CLINC150, it delivers better out-of-distribution detection and lower expected calibration error, precisely because the cheaper stochastic forward pass lets you average more Monte Carlo samples without blowing up your compute budget. You might wonder about the Laplace kernel restriction. It's true that the Laplace kernel is less flexible than an RBF kernel when it comes to controlling smoothness. But the ablation studies show that in a deep kernel setting, where a neural network already learns a highly non-stationary feature map, the predictive trade-off is negligible. The computational gain is massive. The method does trade some flexibility in learning arbitrary, inducing locations for a structured fixed grid, but that's a deliberate design choice for stability and speed. Future work is already looking at adaptive dyadic grids and extending the sparse execution pipeline to broader kernel classes. SIKA-GP is a really elegant example of how exploiting mathematical structure can unlock practical scalability. By turning GP inference into a sparsely activated BNN with tensorized indexing, it removes one of the biggest bottlenecks in Bayesian deep learning. It's not just a theoretical trick. It's a drop-in replacement that works with DGPs, DKLs, and modern transformers, giving you calibrated uncertainty without the computational tax. If you're working on safety-critical AI, robotics, or any domain where knowing what your model doesn't know is just as important as what it does know, this is exactly the kind of infrastructure work that's going to matter. I've linked the paper and the open-source implementation in the description, so you can check out the code, run the benchmarks yourself, and see how sparse kernel approximations can reshape your uncertainty pipeline. Thanks for watching, and I'll see you in the next one.